RockTrue Science is a cross-cultural response to the lack of diversity in STEM fields. STEM stands for science, technology, engineering, and mathematics. RockTrue Science is designed to serve the intellectual need of fallen man while serving the desire for interdependence to better understand our physical world while still pursuing spiritual growth. RockTrue Science seeks to inspire, enlighten, and highlight upcoming and established local and international kings and queens of STEM fields while promoting Black consciousness and awareness of who we are and to whom we belong. Welcome, welcome to another Rock True Science episode. So we're going to be getting into the transition metals now. It's about 29 of them, so it's a lot. So it's probably going to cover the next few weeks or so, probably like into October, but they are extremely interesting. So this group of metals, they're all pretty much metals, and they're all in a solid metallic form. So they end up having like a situation where they all kind of look the same. Like when you look at them, like you really can't tell them apart other than someone telling you this is this metal. And there's a couple of radioactive materials in there as well, but they're still kind of like metal, but they're just radioactive. And there's one that is a synthetic element that is produced from like it's a radioactive byproduct of something else. You know, there's a couple of those sprinkled throughout the table, and there's one in this group, and they're all very funny in how they act, because unlike all the rest of those all the rest of the elements in the periodic table, they have more than just their outer shell of valence electrons interacting and doing stuff in different reactions. They're two outer layers. So they're depending on the size of them, they might have an outer d orbital or an outer f orbital. So both of those orbitals tend to have electrons that get involved in different bonding situations, and so they tend to have a wide range of oxidation states. Oh, excuse me. Whew. I had a lift off tablet, and it's kind of like Alka-Seltzer. And instead of putting it in water, I just like ate the tablet. So it's like it's like bubbling all up and down like my esophagus at this moment. So it's like a lot of blowback happening right now. So excuse me. But that is what makes them very interesting in their chemistry, is really this wide range of oxidation states, and they tend to have a ton of different isotopes that are isolatable. So some elements have isotopes that aren't really easily isolated. These tend to have a ton of isotopes, and not too many that are stable. Most of them tend to have like one or two stable isotopes, and those are usually the ones that are worked with on a regular basis when we're using it in different processes and things like that. But I did find a bunch of information about these. So we're going to get into even how the names came about for, I think all of these talk about where the names came from. And like, that's the thing. Cause like the other ones, like it wasn't nothing like real, you know, fancy with it. Like most of the times, like the name is like what it does or like where it was found. And so a lot of times these have this similar situation, but it's a couple of them that have, it's like for real, like scientists can be some big haters. So it's definitely going to be, we're going to talk about some of the drama behind the naming of these compounds, of these elements as well. So the first one on the list, we'll be talking about 5 of them today. We might get to sneak an extra one in there. We'll see. Is scandium. So scandium is actually named after Scandia, which is the name of Scandinavia way back in the day. So most of these were discovered like in the early like 1800s, late 1700s. So to give you a kind of time frame of where most of these are being found. So somebody wants me to share so you share the show with them. So by a Swedish chemist named Lars Nilsson. And that name Niels is a lot, like you got Niels it's a couple of different Nils guys, but they're not the same person. Just like it's this William Gregor. I was like, why does Gregor sound familiar? And I'm thinking like Gregor Mendel, not the same person. I was like, oh, is that did they like? I'm thinking like Gregor hyphen Mendel, because that could be two different people, and that's just their last names. Like, no, Gregor Mendel is a whole person, first and last name, and he does something completely different from what we're talking about. So, that's that when stuff gets like triggered, the association in my brain, that's how that kind of works out. So, welcome to the maze that is my mind. And so this element, it tends to have a +3 oxidation state. So +3 meaning it is happily giving up 3 of its electrons. So the way the transition metals kind of get their not name. It is a name, but it's really their name when they're in a compound or when they're being referred to like in the actual use in chemistry. So not like Scandium, not that name. I mean like Scandium 3. So they're ionic names and how they bind to stuff. Oh, that's my daughter on her phone. I'm like, what is going on? She's on her phone. But so they'll have the name, and then in parentheses, it'll have the Roman numeral of its oxidation state. So Scandium +3 would be Scandium, and then in parentheses, it would have the Roman numeral 3, which are 3 I's. And then it would have whatever the oxide, like if it's Scandium oxide, it'll be Scandium 3 oxide. And so it's not the same as its chemical name. So not chemical name. That is its chemical name. It's not the same as its chemical formula. So the chemical formula for that would be SC, which is its atomic name, SC or abbreviation. And then it would be 2 because the oxidation state of oxygen is -2. So you would have two atoms of scandium merging with O3. So it changes the oxidation. So they swap. So if it's 3+ on the scandium, then it's going to be a 3 on the oxygen, and then it's the 2- on the oxygen. So it's going to have a 2 on the scandium. So it's going to be SC2O3. So that's how pretty much all the compounds that are made from the transition metals are written in their chemical formulas, and how they're named when you name them. And then there's a couple of different ways that names are kind of come along, like they have common names and things like that, but they're usually referring to the same compounds, but it's just in a more common like industrial use or something like that. They might call it something different, but they might be referring to this actual chemical formula. Yeah, names make stuff all weird and strange, but if you're in the context of where it's being used, then it shouldn't be a problem. And then it also has a +2 oxidation state and a +1 oxidation state, but that state is pretty uncommon. For most of these, the +1 oxidation state isn't that common, mostly because of their electronegativities. They tend to give up more electrons than not. So, yeah. And this is a silvery white, light and soft metal at room temperature. So it probably has like the same consistency as like, say, sodium. And it develops a pink yellow oxidation layer in air. So it kind of gets like a pinkish yellowish kind of like luster to it when it's in the regular open air. So the air, the oxygen and different, whatever, all the stuff that the outside air is made of, it oxidizes the surface of the metal and it gives it a slightly different coloring to it. And then it's used in alloys like aluminum, but it has a higher melting point, and it almost has the same density as aluminum, so that makes it merge better with it. So a lot of alloys tend to have similar densities because it just makes them easier to mix together. And so the way that you would make aluminum harder or sturdier, you add some scandium to it. It's a rare earth metal, mostly because it's found in rare earth ores, but it's not itself rare. So That's what I'm saying. Like the way they name stuff and describe stuff, it can be kind of confusing. But I know y'all following me. And it's the 35th most abundant element in the Earth's crust and the 23rd most abundant element in the sun. So yeah, there's stuff in the sun. It's not just a big, ball of fire up there. Like it actually has minerals and other things molten and melted down in its core. That big mass in the center is actually melted minerals. So yay us. Scandium 46 is a radioisotope, meaning it's a radioactive isotope. Isotopes are compounds that have different numbers of neutrons in their core, so they tend to be slightly heavier. So they have the same number of electrons and protons, but they just have more neutrons, making them an isotope. And a radioisotope is just a radioactive isotope, meaning it gives off, little photons of radiation and stuff like that. And it's used as a tracer to detect leaks in underground pipes and also used to monitor the oil refining process. So, that's useful. Sounds kind of toxic. Scandium iodide is used in mercury vapor lights to produce light similar to sunlight for photography and film. Like, I was like, oh, so that's why, because it's like, I be wondering, I'm like, are they really shooting that in the daytime? So that makes sense now. So sometimes they're not, it's on a closed set and they just put up these big old bright scandium mercury vapor lights and then boom, you think it's the sun. It's not. And the color associated with aquamarine gemstones is due to the presence of scandium. So the great thing about gemstones is that most of the colorations and things like that are due to these metal oxides that are trapped in the crystal or the crystal lattice structure. That's just a sciencey term for how the molecules are stacked together. Okay. That's all. A lattice structure, it has a certain type of mathematical formulation for how many things of a certain size can fit into this type of structure. And it gets real complicated real fast. So we're not going to go that deep into that, but just know that it's how something is stacked together in a crystal. Okay. And so, a lot of the transition metals are the reasons for the different colors for these gemstones, and scandium is directly responsible for that pretty aqua blue dull in aquamarine. And scandium is produced as a byproduct using uranium during uranium refinement. So uranium is one of those nuclear power elements. So when they're using nuclear power to turn your lights on or heat your water or things like that, that's what's being used. And scandium is usually a byproduct of that process. Titanium. So titanium, I love titanium. It's one of the hardest metals, and it's actually the strongest metal with respect to its density. So it's a very light metal, but it's extremely strong considering how light it is. So that's why people love them some titanium. Okay, they don't know where it came from, how it was made. Some people think it's an alloy. It's not an alloy. It is what it is, and it came just like that. And it's actually named after the Greek mythological Titans because of its strength. So there you go. And by the German chemist Martin Klaproth, but it was first found by the geologist Reverend William Gregor. So that's where that Gregor name came in I was talking about earlier. And, and so it mostly, his what is that parish? It's a parish. So his parish that he worked at. So he was a reverend and a geologist, not at the same time. So he was fully submerged in his spiritual duties, but as like his pastime on the side, he liked picking up rocks and figuring out what they were. And so the name of his parish was I'm probably not going to pronounce this right, but it's McCannon. something like that. But he originally named this metal Maconite for his parish, which is where he originally found it nearby. And it was renamed later by the German dude. See, that's what I'm saying. Like that's that scientific, back and forth, the not so not so oops is at your toe. Don't worry, I'm just gonna lean in on it. So yeah, they didn't really, they didn't have the massive amount of courtesies that they do today. They still don't really do that today. They still kind of, I'm gonna leave it at that. But this metal has an oxidation state of +4. Its most common oxidation state is +3. And it also has a +2 oxidation state. And its most uncommon is +1. Like I said, usually a +1 is like not so much as happy state, although it can get into a +1 oxidation state, but usually it's the environment that happens in is controlled. So it's usually something that we did to it that makes it a +1 oxidation state. But it's not going to just naturally occur in a +1 oxidation state. It's hard, it's shiny, it's strong, because it's titanium. Like, it's titanium. It's used in many alloys, and it has the largest strength to density ratio of all the metals. So other metals that may be stronger than it tend to be very dense. So if it's dense, it's going to be strong. Like I said, this one is a pretty light metal considering how strong it is. And it has high temperature resistance and lightweight strength to the alloys that it's added to. So that's always a plus. I'm trying to get this link so I can share. People asking me mid show, like, girl, here we go. And so this is the thing that I like about it. So about the people like that be missing parts of their skull, and they be like, oh yeah, I got a titanium plate in there. Boom, titanium. Like when they say they have metal in their body, it is more than likely titanium, because it fuses very well with bones and it is non-toxic to the rest of your tissue. So you don't have to worry about getting, rust in your body, and then, that's the issue. Or just it basically being, absorbed in your other tissues. Titanium, once it's in there, it stays where it's supposed to be. It doesn't like go and wander off somewhere like other metals would do. So if you need a hip replacement or joints and knees and kneecaps and all that situation, titanium is the metal that they're screwing in there. And because of that, it resists corrosion. Like I said, you don't have to worry about rust. And for that reason, when it was first kind of discovered and most widely used, it's used to fortify ship hulls and things like that. Ship hull. Does this sound like hulls? That's a terrible word. The outside bottom body of the ship. Hey, Marley King. So yeah, because the people who worked in shipyards, they were usually the ones that had to it used to be wood. Go figure. Big giant, these huge ships or whatever made out of wood. Yeah, go figure. So those things tend to get corroded and eaten up by the sea salt and animals and things in the water. That's like, the barnacles and all that stuff. So they had to scrape it and all that. So once they finally made metal ships, it was made out of titanium. Why? Because it's light, so you're not going to sink, because you don't want something that's extremely heavy and going to sink as soon as you put it in the water. So titanium was, the prime metal for all of that: strength, durability, lightweight, and resistant to corrosion and rust. It is the 9th most abundant element in the Earth's crust and the 7th most abundant metal. It is hard to isolate pure titanium. So after it was discovered in 1791, it wasn't isolated in its pure state until about 1910 by a New Zealand metallurgist. These words, man. Metallurgist named Matthew A. Hunter. So these are people doing their thing, probably like melting down ore and stuff like that. And so because metals have different melting points, then you can isolate different metals by heating them to different melting points. So titanium 3 compounds are often violet. So yeah, they tend to have the pretty purples and things like that. We actually did an experiment. I have a slight headache now. We actually did an experiment, I believe using like a couple of different titanium compounds, and then varying the color or the intensity of the purple by adjusting the pH. So yeah, transition metals and acid-base chemistry are like that, okay? They homies. So yeah, that's when we really started getting into the acid-base calculations and things like that. That was I was scrolling through TikTok, the little chemistry TikToks. That stuff was hilarious. And all of them were basically about how people were saying like chemistry was like hard. And it was like, if that's your major, just change it. Like one girl, she was like, yeah, I'm a chemistry major. And then after the first week of class, I was like, yep, I think I'm a model now. So yeah, if you made it to get your chemistry degree, man, look, I understand the struggle. It was definitely a real one. And it is used in sunscreens for UV, to block the UV light. So titanium dioxide, titanium oxides. So and then in my specialty, when I worked in my field in chemistry, I was actually a paint chemist. So I did R&D chemistry at a Sherwin-Williams paint plant, and one of the main ingredients in the paint that we had was titanium dioxide or titanium oxide. And so there were 2 different forms. You had a powder form and then liquid form. Liquid, not really, it's more of a slurry. So a slurry isn't quite all the way liquid, because a slurry is a liquid with a solid dispersion. So a slurry is more of like a solid solution dispersion. So basically what happens is, in a slurry, you have little tiny like solid powder floating around in water or some type of liquid. And then as that stuff sits, the solid will actually settle out into the bottom, back into its solid form. So these tanks are mixed at varying speeds and for varying lengths of time to keep that from settling out. And then just before it's delivered through our system, it's mixed again, and then it's delivered, because you don't want to get mostly water, because then you miss out on the titanium oxide that you need. So the color might be a little bit darker if it's not mixed properly before being added in, and the weight of the paint would be less than, because you don't have these titanium solids in there. So that's one way that we adjusted the brightness, and also like the reflection, so like the luster of the paint. So when you put like a certain type of light on it, how that looks to certain things is affected as well by how much titanium oxide is in it. So it gets the science and the chemistry with that gets pretty interesting, especially in like a practical application like paint. So I thought that was pretty cool, because I was like a super duper like chemistry nerd. And then when I got that job, I was like, I didn't even really have to use like most of the chemistry that I went to school and learned. So that was, I don't know, that was like bittersweet, but I did learn a whole lot of like other things. So that was also very useful. And it's relatively inert, so it tends to be used in hypoallergenic jewelry, so you don't end up with like, the green situation. The jewelry turns green because it's usually a metal that can be oxidized by the oils and things in your skin. So the oils will break down whatever coating that they put on it to make it have that metallic shine or luster. And then once the oils break it down, then the air starts to interact with the metal and it creates that green little oxidation junk. And it can be an itchy situation. So vanadium, that's right. Vanadium, I think that's right. Cause I misspelled it when I wrote it in my notes here. I'm looking like Vandium. That's not a thing. Vanadium was discovered in 1801 by Andres Manuel del Rio of Mexico City. He was a mineral out mineralogy. Yeah, that's right. Like the words, it's like when you think of like where the vowels is, it's like, yeah, that sounds right. Mineralogy professor at a university. It's like basically a dirt university. Like they literally studied dirt there. So I can't remember the full name of it, but they studied dirt there. And he originally found it and then called it panchromium because it had like all of these like pretty colors and stuff. And chromium is next. We'll be getting to that. So chromium is very colorful, so that's why. But chromium was already isolated at this point, so people knew what chromium was and they knew that it had all of these colorful oxides and salt compounds. So that's why he called it panchromium, because he knew it wasn't chromium. And then he later renamed it Erythromium for basically it means red flower. Not sure why he did that, but so this is okay. Now this is where the science drama comes in at. So Del Rio was the first guy to find it, isolate it, name it, call it something, right? Then along comes this French chemist name. I'm not even going to attempt this man's name. He has a hyphenated first and last name. Whoever named him, I don't know, has serious problems. And that's probably why he did this backwards, buttholey type stuff that he did. So then he comes along in 1805 and says that Del Rio didn't find a new mineral or element or whatever. He said it was just impure chromium. So Del Rio, not really, putting up a fight. He was just like, oh, okay, cool. So he withdraws his claim that he found a new element. And I'm just like, why would you do that? You're supposed to be like, you're supposed to say it with your chest, like, nah, I found panchromium, like I said. Like, but he didn't do that. So 20-something years later, in 1830, a Swedish chemist named Niels Gabriel Säfström, he finds this thing called vanadium. So he's the one that calls it vanadium. Okay, and we'll get into what that name means too. And then the German chemist named Frederick Waller behind him showed that they found the same thing. So Del Rio actually found it, but because he didn't put his foot down and say it with his chest, he don't get credit for it. Okay. And so now it's not called erythronium. It's called vanadium. So Niels Gabriel, being Swedish and all, he's from the Scandinavian area where they have the Norse gods and goddesses and things. So that's where that name came from. It's actually the Norse name for the Scandinavian goddess of beauty, Freya. And it's pretty. It is. Vanadium is pretty colorful. It kind of puts me in the mind of like bismuth, how bismuth is like all. Google it. Just Google it and you'll see. It almost looks like if you've seen oil on water, like when it reflects off of, like when light reflects off of oil and water, like car oil. That's kind of the coloring that it has, but it's metal. So yeah. And yeah. So it has a +5, +4, +3 oxidation state. Its most common oxidation state is +2, and it's +1. And it also has a 0 oxidation state, You see how jazzy it gets, right? And it also has, very uncommonly, a -1 oxidation state. So that's what I'm saying. The transition metals be real jazzy, okay? So the one of the, I guess, the regular characteristics of metals that we kind of assume about metals is that they have positive oxidation states because they tend to be, the electron givers, like because they stay where they are. They like to chill out where they are, and when other stuff wants to come and take an electron, it's like, yeah, sure, okay, whatever, we good because we're stable, we're in a solid. But vanadium can also accept an electron, so that is interesting, to say the least. So it's hard, it's ductile, meaning it conducts a little bit. It's shiny, it's strong, it's a blue-gray metal at room temperature. So when it's not heated or it's not like really cold, those are its properties. Pure vanadium wasn't produced until 1869. So it was discovered in 1801 and officially, after the chemistry drama died down in 1830, and then the whole, like, almost 40 years later, it was isolated in its pure form by an English chemist named Henry Roscoe. And he showed that the previous samples, so the ones that the people who discovered it, so Del Rio and the French dude, like, I'm just saying, just from his name, like, I ain't even gonna throw no shade because he long gone. It's cool. Like, I don't know. You can see I feel a type of way about it. But yeah, that they were working with was actually a compound called vanadium nitride. So that's VN. So literally V, which is vanadium, and nitrogen, N. So vanadium nitride. And the Henry Roscoe dude was the one who actually got the pure form of vanadium. Most is used to strengthen steel alloys, and it's used in engine parts, armor plating, axles, and tools. So yeah, that's cool. That's pretty cool. It's and it was used extensively in Model T Ford. So when Ford came along and had his assembly line cranking along, his engine parts and things were made with vanadium alloyed engine parts. It is found in 65 different minerals, and this does not surprise me, seeing its wide range of oxidation states. So that also means that because it has a -1 oxidation state, it can be the anion to another metallic cation. So cations are positively charged ions, and anions are negatively charged ions. So because it can be both, that explains why it's in so many different minerals. It's used in nuclear reactors due to its low neutron absorbing properties. So nuclear reactors deal with neutrons. So the nucleus of an atom has protons and neutrons in it. And when you fiddle with the neutrons, some of them, you pull some stuff out, and the energy released during that reaction is usually what nuclear reactors harness for energy. And the neutron is then replaced to, neutralize that atom again and reuse it. So that's why nuclear energy tends to be looked at as a kind of renewable energy, but it does still have nuclear byproducts and radioactively decaying waste. So that's why it's not, I wouldn't say it's sustainable, it's just renewable. Yeah. And it generates a lot of heat. So there tends to be a lot of what do they call it? Thermonuclear waste. So yeah, that's a problem too. Because when you heat up water, then you have a bunch of hot water. Where does the hot water go? If they dump it into waterways where things are living that normally live in cold water, then you raise the heat, the temperature of the water, stuff starts to die. More things can be dissolved in the water because it's warmer. Like, there's a lot of problems behind that. So yeah, that's another discussion for another day. And it is Also, the vanadium pentoxide, so V2. Remember when I said when it's in a when the oxidation state is kind of passed on to the thing it's connecting to. So when oxygen binds to any metal, it's going to give the metal a 2 in front of it when you see its chemical form. So V2 from the oxygen, O5 from the vanadium. So this is a oxidation state of +5 in this pentoxide. So vanadium pentoxide is used as a catalyst in the production of sulfuric acid. Sulfuric acid is used in a ton of industrial processes for a bunch of different things. And like I said, most metal chemistry is done in acidic circumstances because it keeps, it allows them to manipulate the oxidation state of the metal. And it's also, now this was a strange one. I had to look this up because I hadn't taken like biology in a long time. And we actually went through the whole animal kingdom, all the different kingdoms, like all, trust me, it gets real strange. And this is actually in the animal kingdom. So this is an animal, but it's from the phylum. Like I said, we're gonna get into biology too, because that's a very interesting subject. So it's in the phylum Chordata for reasons that we're gonna explain. Like I said, it gets real it gets real layered. Okay. So this is an animal from the phylum Chordata. It is a sea creature, and it's called a tunicate, which is a sea squirt. So I'm not sure if you like watched the Nature Channel like I did as a kid and even now as an adult. But like when they talk about the sea squirts, they're like those little like oddly shaped. They look like, I don't know if you've seen like people who just like took a pottery class and like they first like kind of pot creations, how it looks all strange and like loop with like a hole, and it's like, what are you supposed to store in this jar? That's kind of what sea squirts look like, but they're like different colors and things. Like they have different situations going on the outside, but that's how they're shaped. And so these things actually have vanadium in their blood. So like how we have iron in our blood, and that's what binds oxygen to it and allows, our blood to carry oxygen. Vanadium is found in proteins called vanabins in these particular organisms' blood. So I think that's kind of cool. It's almost like having an alien on the planet, like in the ocean. It's different. Like I was like, is like, would their blood be a different color? Like, does it make it like green or blue or something? Interesting. And it's actually also an essential nutrient for us, but in very, very small doses, like in trace amounts. Like the amount of vanadium that you're probably exposed to is enough. Like you wouldn't actually have to seek it out or take a supplement because it's toxic. So there's a couple of those like that, like chromium. Oh, and boom, I'm on chromium now. So like chromium is in that same boat. It is an essential nutrient in very small doses, but it's toxic. So chromium, the oxidation, chromium 3+ is actually what we need. Chromium 6+ is highly toxic. So yeah. That being said, chromium is a Greek word, chroma, meaning color, because chromium salts are extremely colorful and they produce very vibrant colors. And a lot of the earlier like pigments and things like that, like it had been used for thousands of years before it was isolated and named and all of that. Like most of the time, like I guarantee you, people didn't even know like why this dirt was this color and that dirt was that color. They was just like, oh, cool. When you mix it with water, I can smear it on here and draw something. So that's kind of how it was. Like they knew how to use it, just didn't know what it was. That happens a lot, doesn't it? Like, hey, what's this? Could be toxic. I don't know. Like, so it is commonly found in is +6 and +3 oxidation states. Like I said, the +6 is extremely toxic to humans, but it's common oxidation state is very easily converted between the two. And it has a +5, +4, a +1, and a 0 oxidation state. The 0 oxidation state is this elemental metallic form, and the other ones, something has to be done to it to create those oxidation states. It's solid. It's like a steel gray, like a I don't even know, like when they like I don't know, like because I can see the difference in the grays, like you can see the difference in whites, but it's like when they put a name to it, you be like, isn't steel gray? So how you gonna be a steel gray? So it's gray like steel, but it's not steel. I guess that's how that's yeah, we're gonna say that that's how that's designated. these these names are we're gonna have to talk to these people about how they name and stuff. like Heather Gray. What is Heather? I thought Heather was a person. Like Heather's a name. So like Heather Gray. I don't know. I don't know. Like I said, I'm not gonna talk. I'm not gonna mess with these people in these color names. Um, it's hard. It's lustrous, so it has like a nice bright sheen to it. It takes a high polish and resists corrosion with a high melting point. So nifty. And it was first used as a red pigment from the mineral crocoite as lead too. So in this mineral, it was actually like together in its chromate form. So CR2. Oh, it probably had some other oxidation state. So like 03, 04, probably 03, CR2, 06 maybe. Who knows? Because I'm trying to think like what's the negative? It would be negative too. So CR2, 07. That's what it is. Chromate. Yes. See, I had to like knock the dust. I had to knock the dust off those like connections in there. Like, no. We okay. We're there. So CR207 has a 2- oxidation state. And so it combined with lead 2 in that oxidation state to, make a neutral. Yes, a neutral compound. So it's not a charged compound. And in this form, that's what the mineral crocoite is. It's lead 2 chromate, which is that situation. And Lewis, I'm probably gonna mess this man's name all the way up. Louis Vogelin, Vauglin. You can try and pronounce that. Yep, go ahead. So he purified the oxide, the chromate. So the chromate is an oxide. He purified the oxide in 1797 and first isolated the elemental chromium in 1798. So he was able to get the chromate out of the crocoite, and then he was able to get the chromium out of the chromate in 1798. But like I said, they had been used for thousands of years before that, whether people knew that's what it was or not. Chromium plus 3 is what we need in our body, and that helps us metabolize sugars and lipids. So it helps us get our energies and stuff, because sugar and lipids are just fats. So different types of fats. So like fatty acids, those count too, I guess, because they're fats. And then, like I said, the plus 6 is super poisonous. Dietary sources of chromium. So of our Cr plus 3, that the happy ion that that we can actually take in and use and not die from, is found in meat, yeast, grains, produce, and supplements. What was that? Would be, I think that's like I'm trying to think of what form the supplement would be in, but most things aren't going to be like just that thing. It's going to be like a chromate or some type of chromium oxide or something like that to stabilize it, because its ionic form is usually in solution or in some type of situation that we can't get to it. So yeah. So in order for our body to absorb it, it's usually mixed in with other stuff, and then our body gets it and then breaks it down. It's like, chromium, I needed this. And chromium plus 6 is actually a water contaminant. It's used to make steel, add color to green glass. make chrome plating. So, like I said, those processes tend to be hot, very, very hot. And then to cool it down, they use water. And then when the water comes along, it rinses this toxic chromium +6 byproduct into the water. And then if that water is improperly disposed of and gets into our drinking water, lakes, ponds, streams, groundwater, that type of situation, then you have contamination of species, ecosystems, us. So that's why people who live near, around, by, in the vicinity of steel mills tend to have very high incidences of cancers, because chromium-6 is carcinogenic, meaning it is cancer causing. So that's why people who work in, around, people's families of the people who work in or around steel mills tend to be very sick in that aspect of having a lot of different types of cancers and genetic disorders. 85% of the chromium that is moving around and used is used to make metal alloys because of its hard properties. Like I said, it's pretty hard. Is this the one? No, but it's shiny. It's hard and it's shiny. So, like, the chrome rims, everybody be so it's sitting on chrome. Okay, that's what it is. Really, you sitting on chrome +6. Yes. Okay. See, I'm a nerd. It's okay. We're all nerding it out here together. And this was actually pretty cool. I had to do a nerd deep dive on this little tidbit, but don't worry, I'll share some of it with y'all. So the red in rubies and the green in emeralds is actually due to the presence of chromium. So, like I said, chromium has these different, oxidation states, and in these different oxidation states, it has a different color to it. So, in one of those oxidation states, it looks reddish. And then another one of those oxidation states, it looks greenish. And so the thing with these particular gems is that the reason why they look like those colors has to do with the light absorption and transmittance. So when white light hits a thing, so let's say when the white light hits a ruby, excuse me, the reason why the ruby looks red to us is because, see, that's that liftoff blowback right there. The reason why the ruby looks red to us is because when the white light hits the ruby, what happens is that the full spectrum of light is hitting. So when you think of light, like you think of, I don't know if you think of a rainbow. I watched the Magic School Bus, so that's why, like, when I think of white light, I think of like rainbow, but it's actually not that. It's actually energy. So light has photons and it's energy, and these energies have different wavelengths. Okay, so you have like really low wavelengths and then really high wavelengths. So it's like it's moving like this. Okay, and then that's what generates the different colors that you see. So the wavelengths of light is it's like, it's vibrating how it's moving. Okay, it's going to look differently to your eyes. So the white light has the full spectrum of these wavelengths, and then when it hits this gem, the stuff that's in the gem, so the chromium that's sitting in it and all of that, is going to absorb certain wavelengths, and then it's going to transmit. So when you look at it, so when the light is coming through and it's reflected back to you, the stuff that's absorbed is no longer there, and then you're only going to see what is transmitted. So for a red ruby, the wavelengths that are absorbed are the very low ones, like in the 400s and stuff like that, and then like the mid-range near like the 600s. Those are the blue, green, yellowish, something in there. Like, it's a couple of different ones that are absorbed. And then on the transmitted side is the red wavelength, and then like some of the cyan range. Cyan is not quite blue. It's like it almost looks teal, but not quite. Like I said, I don't know. Like, these color names, it's just like, bruh, come on. Like, yeah. So if you've ever seen cyan before, or you've seen a splotch of color and then someone said that's cyan, then think of that color. And that's what's actually being reflected back to you with some red. So red rubies aren't actually all red. There's a bluish. Cyan is in like the bluish tint, but it's not quite like vibrant blue when you think of blue. So I don't know. So it's not quite, it doesn't make it look purple, because if it did, it would look purple. Red and blue make purple. So that's why rubies don't look purple, because it's not quite a blue that's in there, but that's what gives it that darker kind of crimson tone. Yeah. And then in the emerald, the same situation happens. Certain wavelengths are absorbed, other ones are transmitted. The ones that are transmitted are mostly like the green and the kind of yellowish, bluish range. And then all the reds and things are absorbed. So boom. That's how light and color works. I don't know. Y'all might want to look up that Magic School Bus episode. That was fun. He was like in the little pinball machine, and then they had the mirrors and the lights, and they had to absorb each of the different like colors using like I liked it. The rainbow, and that's how yeah. Check it out. And so that also made me like think of like other stuff too, the rest of the stuff. So like with diamonds, because I believe this was the one that talked about diamonds too. Yeah, that's the next point. You see, I'm there. So it occurs rarely in nature in its pure form, and is usually found with diamonds. So this makes sense, because when you think of how the crystal lattice structure that I talked about earlier, so the way diamonds and crystals and things stack themselves, so the elements in a crystal is just that element. So it's usually just some type of silicate or just that. So like in diamonds, it's just a bunch of carbon atoms stacked together. And so when you think of the size of carbon is like this, we'll say it's like this, okay? And then chromium is like this. So imagine when the carbon are stacking themselves, guess what's going to get pushed out? Chromium. And so boom, that's how you end up with pure chromium hanging around where diamonds are, because as the diamonds are being formed, the chromium can't fit in the diamond spaces. So then that also made me think, like, so what's the stuff that be in diamonds? Because I'm like, if diamond, like you know, they price a diamond based on its impurities and inclusions. So inclusions are like imperfections on the surface. So like scratches, scuffs, dinks, knocks, like all that stuff. And then impurities are actual elemental things in, you know, stuck in the diamond crystal lattice structure. So in order for that to happen, they have to be smaller or around the same size as carbon. So that being said, most of the diamond impurities are hydrogen, nitrogen, and boron. So when a diamond, one of those, yeah. So when a diamond has like a yellowish color to it, that's because there's nitrogen stuck in there. The more nitrogen that's stuck in there, the yellower, the more yellow it'll be. Boron makes it appear blue. So when you see diamonds and they have like that blue shine, it's because there's boron stuck in the crystal lattice structure of the diamond. Hydrogen, I don't think causes like too much of the like a color. It probably might make it look like cloudy. So cloudy diamonds probably have more hydrogen stuck in it. So the purer a diamond is going to be very clear and colorless. That's why, what do they say? The CCS, CCV, something like that. Basically how they, you know, price a diamond and, you know, give it its certified, how they certify a diamond is its clarity, its cut, and something else. I forget. I don't know. I'm not into diamonds like that. I like all the, like I said, I like all the pretty colorful gems and stuff like that. So like a diamond that has a slightly yellowish color ain't gonna be like, oh my God, who gave me this yellow diamond? Like, and then once you put it in the metal, like if you're putting it in gold metal, then if it's a yellowish diamond, it's gonna be less obvious because the gold from, you know, the gold reflection of the actual metal is going to make it look yellowish anyway. So I would say that's a way around it. So if you know you don't have that pure of a diamond, then just work with what you got. Okay. And yeah. So this thing, it actually okay, so now we're getting into another vocabulary word here. It displays anti-ferromagnetic ordering. So anti-ferromagnetic, basically, so you know iron is magnetic, right? Meaning it's polar. It has one end that has electrons that point that way and another end that has the opposite pole. And so the magnetic property means that electrons move from one end around in a magnetic field to another end, and so they move in one direction. So anti-ferromagnetic means that within the structure of chromium, so if you have a block of chromium, you have atoms that have all of their electrons aimed in one where the Okay, we're back. Quick technical difficulty. So if you have a block of chromium, then you'll have some of the atoms with their electrons aligned in the magnetic pull in one direction, and then the ones next to that will go in the opposite direction, and then the ones like that. So basically it makes it non-magnetic. So because the magnetic pulls end up canceling each other out all throughout the metal. And so when it's put inside a magnetic field, it doesn't respond to it at all because it's neutralized within itself. And then once it gets to a certain temperature, it becomes paramagnetic, meaning it's a little bit magnetic, like not like, oh, it's going to foot, like, no, it's not going to be pulled into, but it will be affected a little bit by a magnetic field. So what happens is that as the metal gets heated up, did I have the temperature on here? Yeah, to about 100 degrees. It's pretty much almost exactly 100.4 degrees Fahrenheit. Then what happens is some of those atoms that are aligned in those opposite directions, some of them will break free of that and start to align in the same direction. And so once those start to shift and move around, those can start to create an interaction with the external magnetic field. So yeah, that's a little bit of physics right there. Like I think magnetic fields and things like that was probably like one of my more favorite subjects in physics. Like everything else was trash because I'm terrible at calculus. And magnetism and stuff, like the calculation of it does require like some calculus and like a little bit of math and stuff, but the concept was very easy for me to grasp once I saw like how the fields and stuff were going. When you got to calculate magnetic fields, like, yeah. That's where the calculus comes in because it's actually 3D vector calculus. So you have, yeah, we're not gonna get into that. Yeah. And so we are now upon our last element in this for this episode, and it's actually pretty cool. It has only a few like little quick facts, but I think they're pretty interesting facts, and I think it ties very neatly into our RockTrue Beats show, which is coming up an hour after this at 8 p.m. Eastern, 7 p.m. Central. Okay. So Itrium. So Itrium actually got its name from the guy, well, actually the quarry that the guy found this ore in. So a quarry is basically where they dig up rocks. Okay. And this town or village called Iturbi is a village in Sweden near Vaxholm. Yeah. Yep, like I said, I'm probably murdering these names, but it's cool. Um, and that's where most of this metal is found. So that particular quarry found that Itrium and a couple of the other transition metals that we'll be getting into as well came from that quarry. So that's cool. By a guy named Johann Gadolin in 1794 from Finland. And it has a metallic silver luster, so nice and shiny. Like I said, it looks like regular metal. Like if you don't know the differences between these metals and how they looks like regular metal. And it's relatively stable in air. So unlike what was that I mentioned earlier? Scandium. Yeah, unlike Scandium where it'll get like a kind of pinkish yellow film on it when it interacts with air, this doesn't really react with the air. So however it looked when you got it, that's probably how it's going to look after it sits out. And except when it's finally divided. So if the shavings from this can ignite in air if it's hot. So like if you're shaving hot metal, who is shave hot metal? I guess like if they're using like an industrial process, they're like, be careful, it's explosive. So if it's really, really hot, so like above 752 degrees Fahrenheit, like that's what I'm saying. Like it has to be an industrial type situation for this to even be a problem. The shavings can ignite in air. So if you shave it off and it's hot, then it will combust. It will react with the air. Okay. So you get sparks and, fizzles and all that. A component of phosphors used to produce the red color in TV picture tubes. See, that's what I'm saying. Like this one is interesting. It gives glass shock resistance and low expansion. So basically, if you drop a like TV or something, like basically that's why your TV doesn't completely shatter, because it probably got some yttrium in it, and it doesn't. And if you I don't know, my TV is hot, like it's a pretty big, flat screen TV, but when it's been on for a long time, it generates a lot of heat. So if you were using regular glass, the glass would expand due to that heat, and it could ruin the frame and all of that stuff. So that keeps it, from doing all of that. And then also the little picture tubes in there would also expand, and all of that could explode, create a situation, burn out, like all of that. And that's why like old TV sets kind of did that, because they probably weren't using yttrium in there at first. And it also, oh yeah, so now we're getting into the garnet. So garnets are a type of stone or crystal, and it can be synthesized, so man-made. And in this case, yttrium iron garnets are used to filter microwaves and as transmitters and transducers of acoustic energy. So I had to look all of that up, because I'm just like, hold on, what's a transmitter? What's a transducer? I know acoustic is sound. All right, so what we doing here? So basically, the difference between a transmitter and a transducer is the signal that it's carrying. So both transmitters and transducers do the same thing. It takes what does it do? It converts energy from one form to a signal that something else is going to pick up. And so really the only difference between them is how much energy you're transmitting. So if you're doing it, and how the distance. So if you're doing it over short distances and it's not a lot, then you can use a transducer, which transmits this energy in volts or millivolts. And then if you're doing like a concert, say, you want to have transmitters, because that is transmitting in milliamps. So amps are like a big clump of volts, basically. So yeah, it's current. So moving voltage, like a lot of voltage moving creates a current. and a slightly, and when you get into like the physics and stuff, moving current actually generates a very small magnetic field around the wires. So that's why wires are insulated, because if you had little metal, like not only do you have to worry about like free electricity just kind of like, zapping onto whatever is more conducive than the wire is traveling down, but you also have these magnetic fields that can get very out of hand and create situations. So the thing with transmitters though is because they're transporting a lot more energy, they tend to get hotter, but they're also less susceptible to outside electromagnetic interference. So like if you have a phone near a microphone, you could get feedback if you're using a transducer and not a transmitter. Like with the mics, if you're talking on a microphone and you get a lot of feedback, is usually because they have the amps turned up too high. And so they have to use a transducer to turn the voltage down. So when you talk, it doesn't like, get that weird feedback sound. And if you're doing that in a concert, then you would want a transmitter because you want to be able to get that as loud as possible. And yeah, so yeah, I had to look that up. But I'm sure Marley King probably gonna end up going into something like that just just because like I don't know how we end up syncing up all the stuff we end up talking about on this show and that show. I promise you, we do not get together 9 times out of 10. I probably like just looked up like most of the stuff that I'm talking to y'all about, so it can be like fresh on the front of my mind when I'm like going over it with y'all. So yeah. Itrium aluminum garnets are used to simulate diamonds. So yeah, not cubic zirconia. We will be talking about zirconium though in the next show. So we're gonna get into that. But this is not cubic zirconium. This is a different fake diamond, okay? And it's used as a deoxidizer for vanadium and other non-ferrous metals. So basically, if some non-iron type metal rusts, Itrium can be used to give it its luster back, basically. It's used as a catalyst in the polymerization of ethylene. So basically, all the plastic that we use now is pretty much polyethylene, and Itrium is used in the polymerization process to create polyethylene. And so that's been more widely used pretty much worldwide. So it's a widely produced plastic, and a lot of it's replaced the BPA or bisphenol A produced plastics, which are mostly polycarbonates. And yeah, that was all bad. So yeah, they found out later that that's carcinogenic. Yeah. So now pretty much most of the plastic that's used to contain food, water, stuff like that, is polyethylene. They probably still do use like BPA type stuff, but mostly in like probably like industrial stuff and to hold like chemicals and stuff like that you won't be trying to ingest or use, be around, soak in, like that type of situation. So that is it. That was a lot to cover, but I learned a lot. And like I said, I didn't even know that they had that type of like scientific drama going on with like the naming and like elemental identification and stuff like that. I'm pretty sure it's a whole lot more stories like that of like how these elements were like isolated and named and stuff. Like, why did that person get the name and not somebody else? Like, yeah, because they said it with their chest. That's why. That's why. So that being said, know that whenever you think you didn't discover something, until somebody can say why you didn't discover it and why this ain't that, then just say it with your chest. Just say it with your chest and give it time. Like, give it time. It's all right. I'm like, okay, I'm gonna give you 10 years to prove me wrong. Because that's how long it didn't even take dude. Like what? Like he came up like 20 or 30 years later, but that's science. But like usually it takes about 10 years for like new information to either confirm or disprove something, especially like if it's something very common or useful or or widely researched and things like that. People tend to put a lot of money and effort into researching, different types of things. But like if it's something like why I feel like I guarantee you how everybody's getting like, all on that health kick and all that stuff. I guarantee you 10 years from now, It's going to be all types of scientific research backing up stuff that people have been doing for thousands of years to not get diseased. Because that's where, you know, the Ayurveda, the herbalism, the naturopathic medicine, and all that stuff has been used for years by medicine women and men, shamans, you know, the village elders, all that stuff way back in the day before allopathic medicine came along trying to take claim. They're the one that tried to come and say, nah, see what y'all actually found was like, no, what we actually was using was the whole plant. And then science came along and tried to use some of the plant and say that theirs is better or purer because it stripped away the rest of the stuff. But the way plants work is they work better as a whole because there's other stuff in there that science hasn't even isolated. There's stuff that goes on in plants that science can't even tell you why it does that, what it is, or why it's even there. But we eat the whole plant. So it's like, huh? So how you made something better from something you don't even know what the rest of it does? It's like buying a video game and then throwing out the game controller because you don't know what it does. And then you wonder why you can't play the game. I'm not gonna play with these people today. I'm not gonna play with them. I love me some doctors. They definitely will get you together if you got a serious problem. But if it's not like an acute issue or something that's real chronic and you need some help to come back off the brink of death, just eat better. Like seriously, get some plants in your body. Plants can undo even damage that doctor says irreversible. I have seen people, I've seen stories and all that stuff of people come back from the brink of like kidney failure. Like their kidneys didn't fail yet. Like they were, you know, on dialysis and they were having problems and stuff, but then they just changed their diet. They stopped eating stuff that put stress on their kidneys, that they ate stuff that helped detox their body because plants are antioxidants. So antioxidants, they naturally detox your body. They take out the byproducts. It's basically like if think of your body like a steel refinery and everything you put in it is making steel. But then steel has all of these toxic byproducts and stuff, and your body don't know what to do with it. So you put some antioxidants in there, and the antioxidants get rid of it. Boom. See? You see how I pulled that metaphor out? Okay. Eating plants, helping the process. All right. See, that's how you know I'm ready for beats. Okay. I'm making up song. I got music going in my head. All right. Okay. So that is RockTrue Science for y'all. All right. Next week, we will be going over another 5 transition metals. Okay. And I'm not going across the period. So we'll end up running into copper, iron, cobalt, all of those people. Yeah, people. Yep. All of them people next week when we go into our next group of 5, because as you can see, it's very information heavy, and then once we get to the more common ones that are involved in more of our biological processes, it will be a whole lot more information, and I want to definitely be able to deep dive and cover a lot of that stuff with y'all. So that being said, when we here, there, and everywhere, we rock truth or nothing at all. Good evening.